Alright, so we're going to look in this lesson at the equation of a line. How do we write the equation of a line in two-dimensional and three-dimensional, in 2 and 3 dimensions? And we're going to look at 3 ways of representing a line in each of 2 and 3D. Alright, so we're going to start things off by looking at this vector AB and a point on the vector R. Now, we're going to start with this statement here, which really draws on the work that we did on collinearity, and that is that I know that R will lie on AB if it satisfies this condition right here, and that is that the vector AR will be some scalar factor or multiple of the vector AB. So that's our starting point. Now we're going to get straight into it by announcing that the vector equation. So we're going to announce that the vector equation of the line AB is, okay, here we go. It's R. Now R represents the point, the position vector R. So the position vector of the point R. R is equal to A, which is going to represent the position vector of the point A on the vector AB, plus some scalar by U, and U is going to be representative of the direction of the vector AB. So if we just pull out each of these elements, R is the, so that's the position, vector for point R. And that point R is going to be xy. A is the position vector for point A. And so that's going to be some known point, x1, y1. That's a fixed point. R is a general point that lies on the line AB, so that's why it's got xy as its position vector. Lambda here is a scalar, a constant, and U is our direction vector. That's our direction vector for the vector AB. And we represent U by U1, U2. Okay, so we're looking at establishing a vector equation for the line AB in general terms. All right, so there it is. That's our vector equation there. R equals. Might not boundary that up just yet. Okay, now if we write this in component form, so written in component form, so component form being what I've just introduced up here, then we rewrite R as written in component form. So R equals A plus lambda U becomes R becomes xy, A becomes the vector x1, y1, the position vector. Lambda by U is U1, U2. So this is our, we're rewriting it now into component form, and that's going to allow us to pull it down into parametric equations. So that we could say which leads which leads to the parametric equations x equals x1 plus lambda u1, and that's just reading off the top line, and y equals y1 plus lambda u2. So there we have our parametric equations. Okay, we could draw a nice proud box around that. This is our vector format. So here we have, let's just be really clear about what we've arrived at here. This is our vector equation of our line AB. It's a vector equation of AB. Over here we have our parametric equations of AB. So we are now really getting into the nitty-gritty of this of vectors. This is where it really all kicks off. Up to this point, we've just been playing around the edges. Now we're getting stuck into the core of vector algebra, and once we've established some equations of lines, then we start to look at angles between them, and then we go into 3D. We look at we looked at equations of planes, intersection of planes and lines. It builds and builds and builds, and the algebra sometimes gets fairly heavy, but let's just take it stage by stage. So we've got parametric equations like so. Now if we make our parameters in equations 1 and 2, if we make our parameters the subject, then we'll be able to eliminate our parameters to just arrive at our Cartesian equations. Our Cartesian equation of the line AB. So let's now go to and by eliminating lambda. So from equation 1, we get that lambda is equal to x minus x1 over u1, and equation 2, similarly we get that lambda is equal to y minus y1 over u2. So from that we can say that therefore x minus x1 over u1 will equal y minus y1 over u2, and that's a pair of parametric. Well, that's a parametric. Sorry, not parametric. That's a Cartesian equation. So we've already established our Cartesian equation here. Remember, a Cartesian equation is just an equation that relates our x and y without a parameter present, or in 3 dimensions our x, y, and z. So this is our Cartesian equation of AB. So that's all well and good. We could tidy this up a little bit. Tidy it up, just rewrite it, and we could have it looking like so x minus x1 by u2, so it'd be u2 by x minus x1 equals u1 by y minus y1, and therefore we could have y minus y1 equaling u2 over u1 by x minus x1. I wonder if that looks familiar, where this is our gradient of AB, And u2 over u1, if you think about that in terms of its gradient, rise over run, u1, u2 was our direction vector, remember? So remember u2, not u2, u1, sorry, u1, u2 is the direction vector. So that's giving us the direction of the vector AB, and as we know, that's u1 represents across and u2 represents up. So up over across gives us gradient, so u2 over u1 here, look at this, y minus y1 equals m basically, x minus x1. That's our Cartesian equation of a straight line, given points x1, y1, and gradient. So that's our Cartesian equation, just written in two different forms. So we could say that that's just two different forms of it. Now, when it comes to writing in 3D, we just stick with the this format here. So in 3D, we end up with x minus x1 over u1, which equals y minus y1 over u2, which equals z minus z1 over u3. That's going to be a really useful outcome. That's as a Cartesian equation in 3D. And we'll come to an example of that. So let's have a look at a few examples now where we bring this stuff into life. Okay, here's an example. We've got points A and B given to us as 1, 3, and 2, 5. So we're going to go through each of the different representations of the line AB by firstly a vector equation, then we'll look at a parametric and a Cartesian. So the vector equation, remember, just starts with our R equals A plus alpha U. Okay, so R is our point, our position vector of R, and that's just our general point somewhere on AB. So we call that XY. So our vector equation looks precisely like this, except we're just going to rewrite it so that A is our general point here, 1, 3. So not our general point, R is our general point. A is our fixed point, our position of point A. We could use B, but we generally just use A. Lambda is what we call our scalar, and U is our direction vector. So what is the direction of AB? Well, that's given to us by A to B, 1, 2. So the direction from A to B is 1, 2. So that is our vector equation. Now that leads into our parametric equation. So we want a parametric equations. So our parametric equations come from this, and then we now just rewrite R as xy, and the rest we just use our vector equation format for. So from this we can just peel off the top line, and we're just extracting our x and our y equations from our vector equation. So x equals 1 plus lambda, y is equal to 3 plus 2 lambda. Okay, so from this equation, we can say that lambda is equal to x minus 1, and from equation 2, we can see that lambda is equal to y minus 3 over 2. All right, and from that, we can say that x minus 1 is equal to y minus 3 over 2, and so therefore we might rewrite this as y minus 3 is equal to 2x minus 2, and therefore y is equal to 2x plus 1. So that's our Cartesian equation, and we've just gone ahead and done it. So that the parametric equations stopped right here. So if we're going to block this off, that would be our parametric equations. Our vector equation was right here. And we already answered part 3 of the example. Cartesian equation. And that is right here. That's our Cartesian. So you can see one peels off the other. Vector equation runs into finding the parametric equations just by rewriting R as in component form as x, y, column vector if you like, and then so that leads us into the parametrics, and then by making lambda the subject in your parametrics, you eliminate the lambda to just leave x and y, an equation in terms of x and y, which right at this stage here we've already got our Cartesian equation, but we can do some sorting out. Certainly in 2D we can. What we should notice from this format here is that we can see straight away from it, by just looking at the numerators, x minus 1, y minus 3, we can see that 1, 3 is there. It's our fixed point A, and the denominators, we haven't got our denominator in here, but our denominators 1, 2 actually turn out to be our direction vector, and that's going to be something that we pick up when we move into 3 dimensions. That little relationship I just referred to there. Okay, so let's now look at a second example. Okay, so now we've got a 3D example that we'll look at. So we've got points A and B again, but we've now got a third dimension, x, y, z points. X, Y, Z coordinates, I'm sorry. So represent the line AB by firstly a vector equation. So let's look at the vector equation, which always starts out R equals A plus lambda U. So by replacing each of these, we get therefore R is equal to A is our fixed point A. So we write that as a component vector, 1, 3, negative 1. Lambda by our direction vector, which is 2 minus 1, 5 minus 3, and 0 minus 1. So there we have our vector equation. Now we want the parametric equation, which leads from the vector format by just replacing R with x, y, and z. And then it becomes fairly straightforward to represent this in parametric form by just taking the top layer, the middle layer, and the bottom layer of this format. So from this we say that therefore x is equal to 1 plus lambda, y is equal to 3 plus 2 lambda, and z is equal to negative 1 plus lambda. So that's our parametric form. So we're parametric equations there. Okay, and then to get to the Cartesian equations, we take from each of our parametric equations, we take lambda as the subject. So lambda here is equal to x minus 1. Lambda in my y equation is equal to y minus 3 over 2. And perhaps you can start to see falling out of this is the position vectors and the direction vectors. By definition, look at what happens here. as lambda is made the subject of the top equation, what happens? We get x minus 1. Now, where does this 1 come from? It comes from the position vector A. Look at where the 3 comes from. The y minus 3 comes from the value of the y coordinate at A, at our position vector, and the z coordinate is in there. Now, the denominators will be, so if I've got some values in here, so 1 lambda just means that I'm over 1. When it comes to that final step of making lambda the subject, here I need to divide by 2, because in here, in my direction vector, my y direction is 2. So I end up over 2. So you can see perhaps how this is peeling off. Now, my final statement here, as a set of Cartesian equations in 3D, I get x minus 1 equaling y minus 3 over 2, which equals z plus 1. So that's my set of Cartesian equations. As you can see, it's a double equation linking x, y, and z. Now we will look at that's a Cartesian equation of a line. When it comes to finding equations of planes, we'll link x, y, and z into a single equation. But in terms of representing a line in 3 dimensions, this is how we do it. Okay, one more example. Okay, so for this example here, we have a line given to us, a line L, given to us, presented to us almost with the final product in what we've been doing, in that we've got the Cartesian equations for it, and we want to extract from this information one of the points and a parallel vector. So one of the points, well, that's a fixed point, isn't it? That's something like this, and a parallel vector, well, that's that guy in there. That's the direction vector. So they're the bits we want to extract from. So what do we know about Cartesian equation format? I'll go back to what we talked about up here, and that is, and it's worth, I think, pointing out now, that in 3D, right, the Cartesian form of a line AB is, and how does it read? It reads x minus x1 over u1 is equal to y minus y1 over u2, which is equal to z minus z1 over u3, where x1, y1, z1 is a position vector, so that means it's a known point, and u1, u2, u3 is there's only one direction, the direction vector. Right, that's a pretty big result that we've established during this lesson. Okay, and remember that works for 2 dimensions as well. So I could have said that's in 3D. In 2D, it's just the first 2 parts of that. That's the 2D version there. All right, but 2 dimensions, easier to get the Cartesian form, because it's just, it looks, it's like y minus y1 equals mx minus x1. But we certainly start by having it written in that form. For consistency, it's a good thing to do. Let's go back to our question then. So how do we, I'm just going to lasso this and push it off to one side, I think. Just move it out of the way a little So we want to rewrite our x plus 2 over 3. So let's get the x plus 2 over 3 equals, so that looks okay to me. I quite like the format of that, but this 1 minus y, I want it looking like y minus y1. So can I write this as, I'm gonna multiply top and bottom by -1. Does that make sense? So I'll have y minus 1 over -2, which is counterintuitive. We don't normally like writing like this, but we want our equation to look like it does here, over to the left. Now my 2z minus 1 is also not helpful because I've just got to have it as z minus z1. So I'm thinking I've got to get the 2 out of there. So almost like 2z minus a half over 1. But again, I don't want the 2 there either. So if I get rid of the 2 and put it over a half, remember dividing by a half is the same as multiplying by 2. Does that look okay? So now the format, I can read off this, I can say that therefore -2, 1, a half, that there is a point on L, and let's have a look at where do we get our direction from. From the denominators u1, u2, u3, and 3, -2, 1/2 is a vector parallel to L. Okay, good. Let's do some practice on exercise 11H, and that's on page 583.